Okay, let's get started. Last day of new material, and hopefully more people show up on Friday. Any questions before we start? If you haven't picked up your exam 4, it's over here. Any questions before we start? Okay, so what did we talk about last time? Templates. And so what is the point of templates? What advantage do templates have over not having them? What, sir? It cannot what other classes? Yeah, that's true, but what is the advantage of having templates over just programming as we normally did? Yeah. Right, yeah. So that's the main advantage, so that I don't have to write as much code, so I don't have to have a separate implementation for something involving integers, one with strings, one with doubles, or user-defined types, or whatever. I can bundle all of them together and just make one function. So if I need to make a change, I only need to do it in one place versus a gajillion places. So today we're going to finish up everything that we need to talk about, and we're going to talk about the STL today. And if we end early, we can start the review for the rest of today before we get to Friday, but hopefully we'll get through everything. So the standard template library, STL, is basically what we've been using this entire class. Okay, well, some of it. So when we write vector of int with the angle brackets, we're using something from the STL. If we're using, in fact, string itself, even though we're not writing angle brackets on them, it's using actually a templated type in the STL. Okay, so in fact, we've been using the STL this entire time. So the STL is commonly referred to the entire library that has some algorithms and some functions that are templated. So like vector or sort, for example, the standard sort function is templated. And we'll actually see that in a bit. So frequently used data structures and algorithms are the ones that are mainly templated are in the standard template library. Yeah, so that you can develop programs faster and more portable if you use the STL, because you don't have to write your own implementation. There's one already in the standard library written for you. And they work with any type because they're templated. So use the STL whenever you can. And we'll be talking about some structures that you can use that can help whatever problem you're trying to solve. So there are two types of things related to data structures in the STL, namely containers and iterators. And you may not have seen these terms, but in fact, we've been using them pretty much the entire class. So what do you think is an example of a container that we've been using for a long time now? A vector, right. It's a container, meaning it contains elements. Another one, in fact, is string. String contains elements. Okay? We actually have been using iterators too. So how many of you have been using the range-based for loop? So on the back end, it's using iterators. So how many of you have written the sort function and then wrote the vector's name dot begin and then the vector's name dot end? Those are iterators too. So we've been using containers and iterators this entire time. Might as well talk about them. So what are containers? Containers is just a black box term or a blanket term for something that holds other things. Okay? So a vector, for an example, is a way of holding a bunch of elements of some type. So a vector of int holds a lot of integers. But there are two types of containers that are in the STL, namely sequential and associative containers. So vector is an example of a sequential container because when I'm putting things into the vector, they are, in our mind, sequentially located in memory. So it's like an array. There are contiguous places in memory. So if I want to put an integer in some place, it's contiguously located next to all of the other integers in the container. So it's a sequential container. How many of you know what a DEQ is? A DEQUE. So this is actually a really, really interesting data structure. So think about vector, for instance. Suppose that I want to insert an integer or whatever type at the very beginning of the list. What has to happen after that? Yeah, I have to shift all of the other elements forward one position to make room for that one integer at the beginning. How much time does that take if there are n integers in the container? Order what? Order n, because I have to shift all n elements one position. I have to look at all of the integers in the vector so far to be able to shift them. Well, what if I just pushed on the back of the vector? Do I have to necessarily do any shifting? No. But what if I have to do reallocation? So like the vector becomes full, I want to push back one other thing. Oops, the array on the back end can't reallocate. I can't put anything in the back of the array. So what do? I reallocate the array and then copy all of the elements down from the original array to the larger array now so that I have room to push back that one element. So often enough, I'm not going to have to do this reallocation, but sometimes I do. So what DEQ is, it stands for doubly ended queue. Okay? So we're not going to really talk about queues, but I just want to show you that this structure is really cool. If you have some algorithm or some process that you need to do where you're going to do a lot of insertions at the beginning or the end of the list, use a DEQ and not a vector. Okay? So what a DEQ does is, suppose that I have these integers at the begin in this DEQ thing. Suppose I want to put in 0 at the beginning of the list, at the beginning of this list of elements. Well, what DEQ does is it actually maintains pointers back and forth. Let's just restrict it to 5 to make it easier. So it maintains pointers of where one element is going to be located next to the other one. So if I want to figure out, okay, I'm looking at the index 1 right here, where is the next element? It's not directly adjacent to me necessarily. Then I just follow these pointers that are in both directions. And so if I want to push on the front of this DEQ thing, let's say 0, then I can actually just put the pointer right here. So one example of this could be I dynamically just allocate 0, the integer 0 and nothing else, and then put the pointer going into the DEQ to the beginning of the DEQ as well as from the 1 back to the 0. And by doing that, do I have to do any shifting? No. But what if I have to insert at the middle of this DEQ thing? Well, I don't know where that middle is because it's dynamically allocated. It might not be in the exact middle position from the beginning to the end like a vector is. So then I would have to chase these pointers one after another until I got to the middle of the DEQ. So mainly DEQ is good for if you're inserting elements at the beginning or the end. List is basically a simplified version of a DEQ. So what I'm trying to get at here is some data structures are good at some things and bad at other things. It's not that one data structure is better than all others at every single problem that you need to solve. Sometimes vector is better, sometimes DEQ is better. So then what we require here is that for sequential containers, we need to be able to randomly access them. Mainly, I provide an index, it's just some random index, and it can find the element at that index, whatever the index actually corresponds to for this container. It may be that it's an array on the back end or something else. We don't necessarily know, but we need to be able to have random access to the container, meaning I put some index, maybe it takes some time, but eventually it'll give me back the element at that index. But the other type of container that is used for other types of problems is an associative container. And so what this is to be able to quickly access elements. And sometimes we need some particular structure about how elements relate to other ones. So I'm going to mainly just briefly mention set and map, because multi-in on both of them is just a generalized version. So what is set? So a set, I think I mentioned this in one of the solutions to an assignment maybe. A set is basically like a vector, but there's no order to the elements and there's no duplicates. So it's not like I can look up index 5 into this set, for example. I don't have random access anymore for set. Because it's what is called an unordered collection. It doesn't have any order. There's no index here. But set allows you to say, is this element in this set or not? And then it can quickly tell me the answer. How long does the question, does this element exist in the vector take if there are n elements? Well, how long might I have to take to check whether something is in a vector or not? Order n, right, because I might have to go through the entire vector. It might not be sorted. So I might have to go through the entire thing. For set, you don't have to do that. So lookups are efficient. So that's what set is. But sometimes you want to have what is called a key value pair. So remember way back to assignment 3, where we had the in and out menu assignment that you had to do. Think about the menu items and the prices. So each menu item corresponds to how many different prices? May seem like a trick question, but it isn't. 1. So there's a 1-to-1 mapping here. Each item corresponds to one value. Each menu item has one price. So that's what a map is. So a map is a container that holds these key value pairs. You have a bunch of keys, you can think of them as the menu items, and the associated prices. And each menu item corresponds to one price. And for maps, they are associative, just like sets are, and they don't have duplicate keys. Because if you think about it, if there are duplicate keys, then they may correspond to different values. And thinking, okay, this key is in this map, but I don't know which value it is, can lead to all sorts of problems. Maybe you do want that with, say, a multi-map, which allows for that. But a map by default has unique keys and associated values. Okay, so any questions just at a high level about what these do? So the main takeaway message here is there are sequential containers where you can randomly access elements in there, and associative containers where you don't have that ability, but they have other advantages like you can look up elements quicker. So we can create containers just like we've been doing this entire time. So we can say vector of string or this other class called list, and they're all templated, so you can work with them just like you've been working with vector. So of course you need to include the appropriate headers for them, but they give you exactly the same templated benefits like vector did before. So nothing special there. So those are containers. What about iterators? So iterators are actually what are called a generalization of pointers. So they behave like pointers, but they have additional benefits. So you can think of them like a wrapper for a pointer. So like how smart pointer was a wrapper over a pointer, an iterator is essentially the same thing. but it has some operations that you can do for them. So there are generalization of pointers, and they have some overloaded operators. So there are different types of iterators depending on the situation that you want. So there are what are called forward iterators, bidirectional iterators, and random access iterators. So the forward iterators are the ones that you can only move forward this iterator through the container. So an example of this is list. So if you look up on what list is what is called a one-directional list, meaning that it only has pointers in one direction to the next element, whereas a deck has them going in both directions. So a list, if you want to access some element in here, it requires a forward iterator, okay? Because if we said it allows a bidirectional iterator, then that doesn't work because list doesn't have pointers in both directions to the other elements. So what container have we talked about today you think has a bidirectional iterator? The deck, right, because it has pointers in both directions. Good. What container do you think has random access iterators? No. So let's go back to this. So associative containers don't have indexes. So you can't use a random access iterator with them. But what do you think should have a random access iterator? So it's not associative containers. Vector, yes. Why is that? Because I did mention that for the sequential containers, you can eventually get to that position, but sometimes you want to be able to get directly to that position. And random access iterators are forced to not go through the entire container and eventually find the element. So I must provide an index, and it must give me the actual value at that index immediately. So list and deck don't have that ability because you have to chase the pointers until you find the element. Whereas with vector, you can do that because the underlying structure is an array. And when you provide an index, it just looks up the appropriate place in the index. So an example of a forward iterator or a container that has it is a list. Bidirectional is a deck, and random access is a vector. Input and output, so we didn't really talk about these, but they are used there also. So if you are reading from a file, you're using an iterator there also. Okay, so if you want to actually write an iterator yourself or like get the iterator for the appropriate container, then you can just say the type name of the container, so maybe list of int or vector int or whatever you're using, colon iterator, and that'll give you the access to the iterator of that container. Okay, so let's just, yeah. So we've been using iterators, as I've said before, by using the .begin and the .end methods. And those give you the iterators of the vector. And so I wanted to show you something really interesting. So I actually copied that from the slides, and you can see that there's some highlighting on the vector int iterator line. Before I hover over it, do you know what that actually will say? Or have an idea? What about this? What if I change this to string? Or in fact, if I change this to long? What else do I have to change to make it work? I have to change the int down here to also be long, right? So that it actually matches. It has to be the same. So what do you think this warning, I guess, will actually say before I hover over it? You should use auto when doing iterators. So why is auto better here? because I don't have to retype anything. And it gets the type right every single time, no matter what this vector's type actually is. So if I put auto here, everything is all good. So this is actually a little interesting. So this is in the slides, but I actually can't see a reason why you would ever use an iterator directly. You always use auto here, because auto doesn't change anything about whether it actually does the right thing. But it has an advantage in that you don't have to re-change the type of the container if the container's type actually does change. So there are iterators in here, but don't use iterators directly. Use them indirectly with auto or the range-based for loop. Use them that way. Don't write them directly, because it's just going to be a world of pain. Okay. But if you are insane enough, or if you are working on legacy code, more likely, you will come across this : iterator thing, because auto came with C++11, which is relatively recent, and older versions of C++ don't have auto, unfortunately. And so people working with legacy code like that actually had to work with iterators, and it was a giant mess. So if you happen to see this sort of thing, these will be good for you. So remember, what are iterators a generalization of? Pointer, right. So in fact, if we use the star operator, what's another name for this star operator for pointers? A dereference operator, good. So this just looks up the element at that position, just like a normal pointer would. So nothing interesting there. But I can do ++ and --- just like another pointer also. And then the end iterator points to the place right after the end of the container. So you can frequently see code like, I'm going to create an iterator, which is the beginning of the vector, for instance. And then while this iterator is not equal to the end iterator. Okay, so sometimes you'll see code like this. So let's just make a for loop, auto iterator equals the vector dot begin. Iterator is not equal to the vector dot end, and then we increment the iterator. So what is this doing? When do I exit this loop? At what point? More accurately, what about this condition? What has to be true of it? It has to be equal to the end iterator, right? If it's equal to the end iterator, what happens? I exit the loop. So what is the end iterator? It points past the end. It's not equal to the end of the container, it's past the end. So if it's equal to something that's past the container, I better stop, okay? So that's why you frequently will see code like this, where it's not like a less than comparison or something. It's like a not equal to, because, I guess for other reasons, but mainly because I want to actually check equality on that last position. Yeah, so you could write less than here, but for better reasons and more portable reasons, you should use not equal to. So this is just mainly for your benefit, because you'll see code like this, yeah. So then this points to the empty memory address. Yeah, right. So you can think of it like, suppose you have an array, and it goes up to the last byte is at some index. The end iterator is directly the next byte. So like the very last byte of the array, and then the end iterator will point to the next one. So it's right after the end of the container. Well, there could be data there, but not in the container that we're considering. Yes, yeah, go ahead.
Would that cause problems with paying pointers, or because we're creating it?
So the container itself actually takes care of all that for us, which is the beauty of using containers. But you can imagine that if you're writing your own container, that could cause some problems. Like if I had an off by 1 error for my end iterator or something. But so maintaining this is actually very important and complicated. Other questions? Okay. So this is just basically what I had, but in a different form. So suppose we have a vector up here, and then we can say we have an iter variable, which is the beginning iterator of the vector. And then while it's not equal to the end, then we're just going to increment it along and then print the value there using the dereference operator. So it's basically just like a normal for loop or a normal while loop here. But so again, I heavily suggest that you use auto instead of writing the iterator yourself. Okay, so I mentioned before that a lot of the algorithms, in fact all of them in the STL are templated. And so they can take something of any type at all and then everything will work fine. But what do you think about like the sort function? So the sort function, of course, can take vectors and the vectors begin and vectors end. Could it conceivably take other things? Yeah, so what is the begin and end, again, of a vector, for instance? What are they, generally? When I say dot begin, what type is that? An iterator, right? So what does a vector have with respect to iterators? Is it a forward iterator, a bidirectional iterator, or a random access iterator? Random access. So let's look at the header, the function sort. So if you look up the function sort, so finally we can actually understand everything about the sort function's definition. So look here. I'll actually zoom in more here. So it says template, and then it says class here, random access iterator. So it's saying we require random access iterators for the sort function. And then sort doesn't return anything, and it takes a random access iterator as the first element, and then a random access iterator as the last element, as the second argument. So remember, do I have to necessarily put vector.begin only and vector.end only for the sort function? Could I conceivably say vector.begin plus 3, vector.end minus 2, potentially? Yeah, as long as I put some random access iterator for where something begins and where it ends, everything will work fine. It doesn't say you have to use a vector here. You don't have to necessarily use a container. As long as you have a random access iterator, you're all set. But notice this. Can a template take anything of any type? So is random access iterator forcing that you use a random access iterator, or could you use a different iterator? I can use a different iterator if I wanted to. So this right now is just a hint to say you should use a random access iterator because everything in the sort function relies on it being random access. But in recent versions of C++, in fact one that's not ratified yet, there are some concepts that allow you to force that right at the beginning, meaning that it'll give you a compile error if you don't, it'll force you to have a random access iterator versus just any old iterator there. Because remember, this can take any class. There's nothing special here. It's just a normal template. So this is why understanding the old stuff of programming languages versus what is coming up is really important. Because understanding how we can use the new concepts to enforce that you, for example, have a random access iterator here is really important. But the really cool thing is that we can now entirely read this header. And so we finally have an understanding of all of this. But there are many other functions in the algorithm header. So there's a built-in binary search function. So there's a built-in count function. So maybe you want to count from some iterator to some iterator how many elements in that range satisfy some condition. So in fact, I'm curious. Let's look at the count function, if it'll load. So let's think about the count function. What kind of iterator do you really need? Do you really need a random access iterator here? Well, for the sort function we did, because we're going to be swapping some elements. You don't know necessarily where they are. But for the count function, all you really need to do is just go through the entire array, or whatever iterator you have. So, where is it? Let's see. Yeah, so it has what is called an input iterator, I guess. But could you, for example, use a forward iterator here? Yeah, because I could just go forward through the range and everything will be fine. Could I use a bidirectional iterator? Yeah, I can use a random access iterator. So some functions are tailored to work with all iterators, and some, like sort, can only use some other iterators. Random shuffle, what kind of iterators do you think that will allow? It's kind of in the name. Random access, right. It doesn't really make, if I'm shuffling elements, it doesn't really make sense to have necessarily a forward iterator. Okay, so here are just some functions. I don't expect you to memorize this, but just understanding. If you see this function, what kind of iterators do you think it supports? So like for count, like this won't be in a final exam question, but it's a good one. Suppose I have the count function which counts the number of elements that have that satisfy some property in a range. What kind of iterators would work for this? And then forward iterator, bidirectional, random access, all three of the above, none of the above. So that would be an example question. But there are other algorithms too. So like max element, for example. So max element will take in a beginning iterator of some type and an end iterator, and it'll just give you the maximum element. And then there's min element, random shuffle, and sort. And that's it. So any questions on STL or anything about templates or stuff like that? Yeah.
So you said that all the sequential containers have random access, but they also, so like for Deck, it has more than one type of iterator, right?
They only have one type of iterator, but actually that's really interesting. So let's try this. So let's look up Deck or import Deck, and then let's make a Deck of ints, and then let's try to do sort of it. So ints.begin, or maybe not, maybe it's not nice to me. Oh, so maybe it does work. Yeah, so that's one interesting thing, because the sort function can't right now enforce that you must have a random access iterator, even though Deck only has bidirectional iterators for its elements.
So even though you can add this to the end of a vector, it's only a random access? Because it said that all sequential containers have random access.
Yeah, let's go back. Yeah, I'm not sure about that either. Let's see. So let's see. Okay, yeah. So it's prefaced on this if right here. So if you can access an element in the container without having to go through the other elements, then it's a random access iterator. Yeah, I should have been clearer about this. So of these three, which ones do you think only have the random access iterator? Vector, right? Because Deck has the pointers in both directions, so you have to chase the pointers along the way. And then list only has pointers in one way, again, you have to chase the pointers. And so vector is the only one that has random access. But could you conceivably write a different container that also has a random access iterator? Yeah, so it's not only vector works with this, but the only one that I know of in the STL is vector. So you're right. I'll probably make an announcement about that. The only one of these three that has random access iterators is vector.
Okay, so you can only have one type of iterator.
Yeah, so each container has exactly one iterator, but which one it is depends on the container. So vector, so the best type of iterator, of course, is random access. But if you can't get that, then you get bidirectional. If you can't get that, you get forward.
So what does list have?
So list has only, what do you think? Forward, bidirectional, or random? Forward, because remember, as I said, list only has pointers in one direction, so I can't go backwards through the list. There are only pointers in one direction. So it only has forward iterator. So I won't ask you about like that sort of thing. Like, does this container, does this specific container have this particular iterator, because you don't necessarily know how it's implemented on the back end. But what I think is much more important to understand is the difference between sequential and associative, as well as what the three iterators actually are themselves, not like which containers have which iterator. Yeah.
And then since the set doesn't have data elements, how do you check the keys?
So I said that set doesn't have duplicate elements.
Okay.
Yes.
It says there it has unique keys but no data elements.
Yeah, so by data elements, they mean values. So remember, map has the keys and the values here. Set doesn't have the values. They just only have keys.
So what does the set look like?
So a set, remember, is something that only has unique keys. So if I include set, then I can make a set of ints right here. And then let's just say ints. There is no pushback method. I think it's add. I'm not sure. Let's see. There's no add function. Come on, C-line, help me. Okay, it won't help me. Let's go into, oh, it's not there either. Where are you? Yeah, let's go into the containers section. Okay, the Wi-Fi is slow. But yeah, so that's how a set will look here. There should be a, so if we look in set, let's see. Oh, so it's called insert. So if I dot insert 0 here, then this just puts the element 0 in the set. If I try to insert 0 again, there are two ways that you can go about this. You can say, yeah, it's already in there. I'm going to fail, destroy the program. But the way that insert works is if there's a duplicate element in there, then it'll just ignore it completely. Okay? So set is, you don't know necessarily how set is implemented, but just know that it has no duplicate elements. Yeah. Okay. Other questions?
Okay.
Yeah.
This might not be important. So since they don't have random access, that means you can't access them in brackets, or is that?
Correct, yeah. So there's no square bracket operator for set. The only way that you can access them is through iterators, and the best way to do that is through the range-based for loop. So if I say auto lm in the set, in the set name, which is ints, then that'll work just fine. There's no square bracket operator here because it's unordered collection, just like map is also. But of course, you can write your own custom vector class that has no duplicate elements, but also has the square bracket operator. So it depends on what your use case is. Yeah. So if you want to not have to write your own custom vector class that enforces that there are no duplicate elements, that's an additional benefit. But one even more important benefit is if I'm doing insertions into a vector, then I may have to shift a lot of elements, which could take a lot of time. Or I might have to do reallocations. With set, you don't have to necessarily do that because the checking of whether some element is just in the set is much faster than for vector. So there are trade-offs to using one container over another. Vector is really good at pretty much everything, except if you need to do a lot of insertions or lookups. So sometimes you want to use set, sometimes you want to use map. It also depends on how your data relates to your other data. So like for the menu application, a map would be the best solution because each menu item corresponds to a price. It doesn't really make sense to have two separate arrays where one corresponds to the items, one corresponds to the prices. Another example of a map was in, what assignment was it? So remember assignment 6, the dreaded assignment, where you had the scores of each of the characters that the user inputted? Which of these data structures do you think would be best for that? Map, right. Because, in fact, not map. Which one's better than map, even? What do you think the multi corresponds to? It's where you can have duplicates of elements, too. So why is multi-map better for that assignment? Yeah, because some of the letters that the user inputted could be duplicates. They can have multiple A's, for example, or multiple B's. So a multi-map would actually be a better solution for that. So figuring out which container is best is actually really, really, really important. But any other questions about this? Okay, we can start the review 8 minutes before the end of class. So do you have any questions about material or something that you're confused about or want me to go over? Or I can let you go early. Yeah.
Sorry. Can you go over big O notation?
Yeah. Yeah. So, and I think that's the concept that most people didn't understand. How many of you do not understand big O notation? Okay, good. So questions like that are what I expect on Friday. So let's go back to big O notation. So yeah, but it's basically from this analysis stuff all the way down. So what do we want to do with algorithms? We want to choose the best algorithm, right? The one that is the lowest cost in general, okay? So if I have an algorithm, two algorithms, one that takes 1 billion iterations for some data set, and the other one takes 1,000,000,001 iterations for the same data set, does it really matter which one I pick? No, because, and if I scale this even more, the difference, the relative difference between them is quite small compared to the overall size of the input. So what we want to do is, what is the trend of what is the performance of this algorithm for larger and larger data sets? So if I look at the performance of some algorithm, it's conceivably going to keep going up. And then if I look at another algorithm, it's also going to go up. What we want to know is there really a difference between these two? So are they growing at the same rate or at different rates? That's all we really want to know. So if we look at this algorithm right here, these two lines at the beginning only are executed one time. But I remember that there's an error in this slide and I didn't fix it. But think about that there's a index plus plus somewhere in here. So this outer loop will be run n times because while index is less than n, if I increment index every single time, then I'm going to do n incrementations of index. So this loop will execute n times. And then there's stuff in the middle which for each of those outer iterations will execute once, or at most once, in the case of the if statement here. So understanding the exact performance is important, but also understanding what is the general performance of this algorithm. That's important. So if we look at something called algorithmic complexity, which is how do these two runtimes relate to each other, then that can give us some indication about which algorithm is better in general compared to another one. So if you remember one of the questions on the midterm, I forget which one, but I had one algorithm that took like 2n iterations and then one that took 3n iterations. So what is the algorithmic complexity here of those algorithms? Is 2n the same as 3n with regard to this, or is the 3n worse, or what? They're the same, because whether you look at 2n over 3n or 3n over 2n, it's going to approach some value, some fixed value, and so the relative difference is exactly the same. It's not like one is going to continually to get worse relatively to the other one. But if I had 2n and 3n squared, now what happens? So 2n is going to look like this, and then 3n, it may start below, but eventually it's going to catch up and go to the moon. So if we look at 3n squared over 2n, does that approach a value if I make n larger and larger? No. So it's going to keep going up and up and up, and the relative difference goes up and up and up. And so what can we say? Is the 3n squared one worse than the 2n, or what? Yeah, because at some point, not for all n, but for some point, the 3n squared is going to catch up and be worse than the 2n. Okay? If we had it the other way, where we had 2n and 3 log n or 3 square root n or something, then does it flip the other way? Relatively, yes. Because one of them is going to look like a line, and the other one's going to maybe start above, but eventually it's going to catch up to the 2n one. So understanding when two algorithms are equivalent versus one being worse with respect to this than the other is important. So big O notation is, informally, G of n here inside the O is worse than f of n, or at least as worse, but definitely at least as worse as f of n. So just as an example, so let's look at several functions. So let's say that f of n in my example was 2n, and then g of n was 3n squared, for example. Is g of n big O of f of n? No, why not? Which one is the worst function here? G is. So I said that the worst function goes inside the O. Is the worst function inside the O? No, so this is no. What about f of n is big O g of n? Yeah, because the worst function is inside the O, yeah.
You mean big O, you mean like dividing?
No, this is just a terminology for saying, I could go into the specifics of what this means, but in general this means the worst function is on inside the O and the better function is not. That's all it really means. So that's true. What about this one? So f of n is big O of f of n. Yeah, this is also true. So the worst at least function goes inside the O versus on the outside. So bear that in mind when I change this back to 3n. So what happens to this no right here? It changes to a yes. Good. What about this yes? It still says yes. This one's always yes. So every function is big O of itself. What if I change this to 3 square root n? Which one changes to no? Remember, the worst function has to go inside the O. The second one. Yep, because the worst function is f of n in this case, and the better function is in the big O, which is not the right thing to do. What about the last one? It still says yes, because every function is big O of itself, yeah.
So on the exam, you were using big O notation without having two functions. Like you were supposed to say the big O notation of.
Yeah.
So how does that apply?
So I'm not necessarily going to set this equal to something, but I'm just looking at the general performance of some algorithm. So in the case of like bubble sort, it's something like n squared. So then like on a test for, like on that test, you would say the runtime for bubble sort is big O n squared. So you have to understand what the runtime of the algorithm actually is, and then say, is big O of, you can just say what that actually is. Other questions? Yeah. Not specifics, but yeah.
Are you going to post the answers after it's due?
Yeah. So the quiz answers will be available on Blackboard after the due date and time, just to be fair to everyone else. All right, I'll see you all on Friday.